Hi everyone, this is Jianyu Wang. Today I'm going to give a topic of enabling precision or recall preferences for semi-supervised SVM training. So first, this is a semi-supervised SVM training, so as usual it will use the standard SVM training. And then I will discuss the semi-supervised SVM training. And then I'm just going to add the precision or recall preference as mentioned in the paper, and I'll show the experiment result. So first it's the SVM training. It has already been discussed in the class, so I'm just gonna briefly introduce it. So the SVM training is to find a hyperplane which separates the positive instance from the training set with the maximum margin along with the minimum misclassification. And this problem is equivalent in solving the following optimization problem. So this is objective function, this is the margin, and this is the penalty. So for the semi-supervised SVM training, the difference is that at first it also trains the SVM module as same as the traditional SVM module, and then it will introduce the unlabeled instance, and then it will classify those instances, and it will switch the labels of the classified set and then retrain the SVM module, which will reduce the objective function, and then this will be repeated until the objective function is minimized. In the semi-supervised SVM training with the preference setting, it's called PSVM in the paper. So before it's classified to the unlabeled set, it will first divide the label set into training set and measure set, and then in the training set it will just train as usual, and then it will measure the the measure set to classify the result and compare them with the label, and to get the precision rate and the recall rate. If the precision rate is not satisfied, it will adjusting the decision value to until the satisfied precision rate and the recall rate is get. And if both are satisfied, it will try to maximize the F1 score. After the module is measured and adjusted, it will run the module on the unlabeled set as semi-supervised SVM. So here is the pseudocode of the PSVM, and the labeled instances is divided into A and B in here, and the unlabeled instances is denoted as U, and the penalty parameter and the kernel parameter as the standard SVM module. So here is the positive set and negative set, and so first it will put the A and B, the labeled instance put into positive and negative, and then it will train on the AR set and adjusting them on the measure set, and then it will classify the unlabeled set and then put them into the positive and negative set. Here is the more clear view with the images. So given those instances, so here is the optimal hyperplane. So at the start, because the set is divided into the training set and measure set, so the training set is like those, and then the hyperplane is far from the optimal, and then to just adjusting on the rest of the measure set, the materials, and it will be iterated until the final hyperplane is found. It will be much closer to the optimal hyperplane. And since before the semi-supervised the procedure has started, it has already adjusting the module on the labeled set, then the efficiency has been improved, and the running time as shown on the figure, it is much lower as the PSVM compared to the standard semi-supervised SVM module. And to the experiment result, the instances also choose using the satisfied recall rate, and the F1 score is a little bit higher to the baseline of the standard semi-supervised SVM model. So to summarize this paper, using the selection of the instance before classifying the unlabeled set, and during the training set, adjusting the value so that the F1 score is improved, and to get the satisfied recall rate and precision rate. And then it's also improving the running time because it is using the subset of the instances. And in the experiment, it also improves the classified rate. And then here is my reference. Thanks for listening. And if you have any questions, feel free to contact me from email or just put them on the discussion board. Thanks.